All right, welcome back. So this is LeetCode with me. Right now, I'm going to be talking about doing a system design, and the topic for today is going to be design a rate limiter. Let's talk about so a rate limiter. If I think we should all be pretty comfortable with what a rate limiter actually is. What it is basically and specifically what we're going to focus on is we're going to focus on a rate limiter between, because there's lots of potential rate limiters. This is going to be a high level design for a rate limiter that we can put into our microservice architecture to protect our microservice. Um, Against external traffic coming in from like a public API. So what we want is, so we have functional requirements, protect our microservice architecture from spammy users. So we want per user or session rate limiting. We want this to apply to multiple microservices. Let's say 5 microservices. Um, So protect our microservice architecture from spammy users per user or session or per session rate limiting. So we want this to be fine-grained rate limiting, and we want this to apply to multiple microservices within our system. We'll say 5 microservices. And what other functional requirements do we have? I think that this is pretty good. Um, Maybe we want configurable with multiple um, rate limiting strategies. And today we'll talk about fixed window and sliding window. These are kind of the basic two. So then we'll talk about non-functional requirements. So the first one is that um, we definitely want this to be highly available. We do have some locking considerations. So we do have some we do have some, um, uh, we need to do, but we do need locking on um, our rows for our rate limiting. So we just need to be aware that um, uh, we also have it. We also have some accurate, highly available and accurate. I won't go too much into this. It's not really like typical. This isn't really like a typical cap theorem kind of. I mean, it is, of course, everything requires a cap theorem type question. But what we want, the net result is that we want basically a highly available system with accurate counts. The other thing that we want to make sure is we want to make sure that we want it to be fault tolerant. If the rate limiter not available, just allow the calls. So what we're doing here is we're making a choice here that basically, if we have any sort of issues with our rate limiter, if the rate limiter goes down, we don't want this to be a point of failure for the rest of the system. And there's some situations in which case you would want the rate limiter not being available to actually cause the calls to fail. But in this case, we're just going to say if the rate limiter is not available, we want to allow the calls. And that's going to lead to some key architectural decisions as well. And what that means is that also, as we come back to this first requirement here, we are highly available as much as possible, but we actually do want to prioritize consistency when it comes to cap theorem because um, we need to do lock rows for concurrent writes. So this is a key thing. So um, we don't need uh, cross node consistency necessarily because we can partition our um, store such that we can such that we can just do that consistency locally. So we lock those rows locally. So all of that is good, but we do need to lock the rows for concurrent writes. So fault tolerant. Um, if the rate limiter is not available, we just allow the calls. So we may have periods of time where the rate limiter, we're obviously developing a highly available system, but we want to make sure that we have a system such that we do preserve this. Um, uh, we do a best effort rate limiting, if that makes sense. Um, cap fault tolerant latency. We want the rate limiter to be super fast. So we're going to say under 10 milliseconds additional latency, but so we want it to be single digit. Yeah, we don't want this to, gum up the latency of our application at all. We want it to be really, really snappy. So this is definitely going to impact our design considerations. And so I guess in terms of our deciding between availability and accuracy, we were wanting to tend towards availability. So that's just something to be to consider in this. Um, so cap theorem, fault tolerant latency, and scale. So in because this is like we are not designing necessarily like a product, we have sort of like some different considerations. We don't really know too much about the details of of the systems that we are actually rate limiting, but we should say that we are going to handle 100 million. Let's say we're going to handle 1 billion calls per day. Be able to handle 1 billion calls per day. Um, yeah, so that's good. Non-functional requirements. And yeah, this is sort of like a infrastructure architecture question. So core entities doesn't really apply so much, as well as API design doesn't really sort of applies that much. Basically, we just want to understand our data flow through the system, our system flow. So basically, in terms of understanding our requirements, so we basically have, we'll just talk about that. So client makes a call to some uh, like API gateway. API gateway then checks a rate limiter. Um, this will return a 200 or 4 or 429, I think is the rate limiting. 423. I'll have to check on that. 429. We'll say 4. It's a 4x response. I'll have to check on it specifically what that error code is when it's rate limited. If it's not rate limited, so I'll say API gateway um, or some sort of reverse proxy. right? And we'll actually go into the some discussions about what that means. And then we have our microservice API. So if we get a 200 back from the rate limiter with the input from the client, and then we can determine uh, this will determine based on the microservice API that we want to hit, and information in the request whether or not we want to forward that along to the microservice API or we want to continue. And then the microservice API will actually run, and then we return to the user. So this is kind of our system flow. So now that we've got this established, we've established our functional requirements, we've established our non-functional requirements, we've established kind of a flow of what we kind of expect this to look like. Let's move on to the high-level design. So we have our client. Um, so we're going with a microservices architecture. So I'm going to say that we have an API gateway here. And then we have some microservices. And these are the ones that we actually want to microservice A. These are the ones we want to rate limit. So A, B, and C. So our client, so without rate limiting, we would talk to API gateway, and then we would have these different microservices behind the API gateway. The next thing that we need to do is we need to figure out how to introduce a rate limiter here. So one option that we could do is we could have an API, or we could have a rate limiter here. So we have a service that is our rate limiter service, and it acts as a reverse proxy. So API gateway just forwards the request along to rate limiter, and then basically rate limiter does some rate limiting, and then it forwards the services, the requests along to the different microservices depending on the configuration. So we're actually moving some of the routing logic from API gateway into this rate limiter reverse proxy. So reverse proxy. Um, and then uh, and then we have this route to our different microservices. Um, so this actually works, and we'll talk about how we actually functionally do the rate limiting in a second. But this would work, and this is a viable design, and definitely some um, companies out there are using something exactly very much like this. This be just sort of a thin layer um, uh, web server, reverse proxy web server that just routes these requests along and does some middleware rate limiting on top. But why would we not build this on API Gateway? So what does API Gateway provide? API Gateway provides um, TLS termination. So routing is a key one, but in this case, we wouldn't be using it. Routing TLS termination, DDoS protection. It does provide rate limiting, but coarse-grained. So that's an important consideration here is that API gateway would not satisfy our functional requirements that we want per user or per session rate limiting. So this would not satisfy the functional requirements. Um, the other thing that we can consider doing is, so API Gateway actually supports, so I'll do this. So API Gateway supports rate limiting, uh, custom rate limiting with Lambda. So one option that we could do is we could introduce our rate limiter here, and we'll have this be a Lambda. So we could introduce our rate limiter here, and then have AWS gateway call out to rate limiter. It has some like it has a basically a way to add a Lambda hook to the API gateway. But this is a problem because Lambda actually has a cold start. So cold start. So this would not good for latency non-func. So this doesn't satisfy, and a cold start can be seconds actually. If we have a spike in traffic and we get all of those requests, we can have a cold start of seconds to actually spin up these lambdas to in order to do the rate limiting to determine whether or not to forward those requests along to our microservices. So this isn't good. We can do like have a warm pool of lambdas. We can actually make sure that we have like a quite sufficient warm pool of lambdas and all that kind of stuff. And all that is good, but we do need to be aware that this cold start is a problem. So we're going to say that this is not good for our latency non-functional requirement. And so we're not going to do this solution. So the next thing that so the other thing that we can consider is that we want to apply to multiple microservices within our system. The reverse proxy solution works well for that. So going back to this solution, we have a reverse proxy that does rate limiting. So this is a microservice that we own and we scale, and basically this reverse proxy is going to actually perform the rate limiting and then forward off to these different services. And so our um, so this description that we have here is for API gateway. Um, and then this one that we have here, the reverse proxy, is just reverse proxy is just responsible for rate limiting and routing. So that works pretty well. The other option that we can do is we can set up, there are solutions out there that handle this sort of thing really well, handle sort of middleware that does this rate limiting, handles system resilience guarantees and reliability guarantees and all that kind of stuff for you, and has a lot of like hooks and stuff that are actually used and are also built in production for handling extremely high volume and like super high scale and distributed microservices architectures. And one of those options is actually called Envoy. And so for this, I would use Envoy. And then here, I would have this be actually a managed Envoy. So we can just deploy Envoy on our own and self-manage this layer. Or we could use AWS App Mesh to manage. And using AWS App Mesh would help us manage our operational load. And what we can do with this Envoy is we can just configure it. And this, an Envoy versus API Gateway. API Gateway is great for public-facing APIs. It provides a whole bunch of amazing functionality for doing that. What Envoy does is it allows us to provide a lot more fine-grained customization and configuration than API Gateway allows us to provide as a reverse proxy. So actually using both can be an advantage because we have specific requirements. So because we have requirements for like per user rate limiting, per session rate limiting, um, Envoy is highly configurable, so it allows us to dig into those nitty-gritty little details like that. So we can configure Envoy to when it gets a request, it will act at the L7 layer, the application layer, so it has access to all of the details within that request. And then what we can do is we can forward that request along to a rate limiting service. And then our rate limiting service, we'll talk about the implementation of that in a second, but just keeping things simple for now. So our rate limiting service will call first. The rate limiting service will do our rate limiting. It'll either return a 400 or a 4xx request to Envoy reverse proxy. And then based on that response, we will determine whether or not to managed. Um, so this is going to provide rate limiting. This also provides other things like resilience guarantees. So this means circuit breakers, retries, lots of stuff. It provides a lot of really cool stuff that we can do. So first we go to the rate limiting service, and then we get the 200 or 400 response back. We get a 400 back, we return that all the way up to the client. If not, we then will forward that along to the relevant microservice, which will do the operation for that we need to do within that that the client asked for. So all of that is good. So you might still be asking, like, why do we have both API Gateway and Envoy Reverse Proxy? Well, they provide different roles. So API Gateway is our public-facing API, and so it's going to provide this TLS termination, DDoS protection, coarse grain rate limiting, maybe on the API key level, or maybe we just want to have this not do anything, and we manage all of that reverse proxy so that we have good separation of concerns. So we can pick and choose which features we want each layer to support. Envoy is also built in C++. It's extremely fast. So this is extremely minimal latency overhead. And all we're doing essentially is forwarding this along to our different microservices. Having this be managed by AWS App Mesh also means that we have lower uh, lower operational overhead of managing this Envoy. So then let's talk a little bit more about, let's get into the actual details of what our rate limiting service actually needs to do in order to perform the limiting. So rate limiting service is a horizontally scaled service. So this one also, kind of don't always draw these, but I'm going to draw this here. We have a load balancer here, and this is an L4 load balancer. So this is just a GCP load balancer, which is going to route those requests in a round robin fashion to our rate limiting service, which is a horizontally scaled service. Our rate limiting service is going to have going to talk to a data store. We're going to use Redis here. Redis is in an in-memory database, and so it's extremely fast and powerful for this particular type of operation. Redis is going to be sharded, and we'll talk about that in a second. But we'll say Redis shard A, Redis shard B, and we're also going to have some replicas. Shard A, replica 2. So these are read replicas. Okay. And we'll get more into the details of how we're going to shard and replicate Redis in a minute. But I want to talk first about how we actually do the rate limiting operation. So what I want to talk about is there's two different ways that we could do rate limiting. The simplest is called fixed window. And in Redis, basically what we have is and the data type for a fixed window is going to be a hash map. So first, I'm just going to lay out. First, we're going to talk about fixed window. That's our simplest approach, and then we're going to talk about our sliding window, which is a little bit more nuanced, but it's pretty simple. It's a little bit more complex than fixed window. It's pretty simple, but it's also much more accurate than fixed window. So let's talk first about fixed window. Um, so basically, our a Redis data type is going to be a hash or hash map. And basically, what we're going to have is we're going to have user, we're going to have API, user, um, and then uh, bucket, basically, as our key. And then our value is going to be a counter. So it's just an int. And so our bucket is just a time window. So for instance, if this is the minute, we would just have like the minute ID for this particular API and user, and then we have a atomically increasing counter that will essentially count up the number of uh, ticks within this particular minute. And if we exceed a certain threshold, then we will return that we cannot do that. So we could have a simple Lua script within our Redis shard that will atomically check this counter and increment it. And if, well, we'll atomically check this counter, see if it's below the limit for this particular bucket. If it is below the limit, we will increment it, and then we will return 200 all the way back to the reverse proxy. If it's not less than 200, we will, or if it's not less than the maximum, or if it is less than if it's greater than the maximum, we will basically leave the counter as is. I mean, we can still increment it, but we will essentially return a rate limiting error code back to the reverse proxy. So this is our simplest operation, and again, we're using Lua on Redis for um, uh, for locking or atomic rights. Okay, so sliding window is a little bit more nuanced. So we have a hash map, but the value in our hash map, so we have a Redis key value store, so we don't need to say but the Redis data type is a sorted set. And the sorted set is timestamps. So key is going to be key, our key is API and user, and our value is a sorted set of timestamps. Lua, again, on Redis for atomic rights. Um, and basically what we're doing here, our sort of algorithm for implementing a sliding window. So here we have a fixed window. We are atomically incrementing this counter. But the problem is, imagine we're doing it for every minute. We allow 3 requests per minute. And then we have one request. We have 3 requests at minute 59. So we have API, user, and then we have minute is 1, and then we have 3 requests at our limit is 3. We have 3 requests at second 59 of minute 1, right? So minute 1 is at 3. And as soon as we move to minute 2, we start over at 0, right? And we get another request. Well, since these 3 requests happened at minute 59, and this new request came in at, at second 59, and this new request came in at second 1 within this minute, then we have a problem here because we actually allow twice as many requests as is allowed. So Um, the trade-off is low accuracy, so we cannot actually allow 2x bursts. So maybe this is okay for our use case, depending on our accuracy requirements, but this is actually much higher accuracy, uh, higher accuracy. And it's pretty simple to implement too. It's not really that complicated. It's one of the easier ones. This is the easiest one. This is a sort of a medium one to implement. So something to consider there. So what does this actually look like in terms of our implementation? Basically, what this does is we're going to have a sorted set. We have a sorted set of all of the timestamps in order. And then we are essentially in our Lua script, we are going to first, what we want to do is we want to look at this API user ID combination. We want to get the sorted set for that. And then essentially we want to, step one, remove everything from the sorted set out of the window, before the window. So we're going to do our timestamp minus we're going to do the window minus the current timestamp. So that's our oldest possible request. And we're going to remove that all from the window. And Redis has this a really nice um, uh, API for doing that, which essentially does that all in a single operation. And the time complexity of that operation is m, which is the number of elements to remove, and log n, which is the elements that it's the logarithmic for the timestamp that we're searching for. So pretty efficient operation, and we get to remove that from the set. Um, then we want to add the new timestamp to the set. Then we want to determine if the number of items. So we'll basically do return allow if number of items is less than the limit, right? We just say return if number of items is less than the limit. It's a very simple algorithm. Basically, we're clearing everything that's expired, everything that's outside of the sliding window. We add the new timestamp, and then we will return if the number of remaining items after adding and removing is less than the limit. And then we return that true. And then this is a Lua script within Redis. So we're doing all of these updates atomically within one Redis shard. So let's talk about our sharding and replication. So Redis, first of all, we're going to use something like Elasticache to manage Redis. We're going to have a multi-AZ deployment. So that's the first thing. So this using Elasticache, I'm obviously a big fan of using managed services so that we have so that we basically reducing our operational burden, reducing the cost of actually managing these different services ourselves. So Elasticache managed Redis multi-AZ, what this means is that we're going to distribute this across multiple data centers. So that's going to be really useful. The other thing is, so we have Redis Elasticache. We want to, we're going to use single leader replication, which is the mode that Redis supports. So we have single leader replication. We have, this is our leader node, and then we are basically reflecting these writes to our to replicas. So here I have pictured one replica. We'll probably have at least two replicas, at least two replicas, read replicas for failover. What that means is that if this primary leader goes down, one of these replicas can take over. And so we have a minimal inter time of interruption where we're switching over from our shard to our replica. If we might have some delay where we do that. If Redis goes down for some reason, then of course we will. Well, actually, let's get to the fault tolerance in a minute. Single leader replication, and then we'll shard based on key, which in our key in either of these cases, API user bucket and API user in fixed window and sliding window. So all of that is good because we're only ever accessing a single key. That's totally fine to have them sharded based on key. There's no reason that we really need to partition more than that, and we can manage this cluster based on sharding based on key in all cases. So all of that is good. Now we have a great strategy for rate limiting. We have two different strategies to pick from. I think sliding window is going to be our default because of the higher accuracy guarantees, and it's not that much more complicated to implement and not that much more expensive to run. So this is a very nice solution that gives us high accuracy and everything like that. Yeah, we have managed Redis, we have single leader replication, we have sharding based on keys, so we have really good reliability on our Redis. So let's talk about go back to our non-functional requirements. Cap theorem, we need to lock rows for concurrent writes. So that's happening within a single shard. So we're not really talking about um, network partitioning here. We're just talking about locking locally for within a single shard. So this is actually a highly available system. So we're not doing any sort of like distributed transactions here or anything like that. The other thing that we want to make sure that we do is we make sure that we are um, yeah we have um, so all of that is good. So the next thing, so we talked about cap theorem, prioritizing availability. We do lock rows for concurrent writes, but this happens on the same shard um, within the same Redis node, basically. So fault tolerant, we do have atomic rights, basically. Fault tolerant, if the rate limiter is not available, just allow the calls. So that's an important configuration that we do in Envoy reverse proxy. If for whatever reason we cannot get an answer or we get some sort of unexpected 500 error code from rate limiting service, our result is just going to be to forward these calls. So in essence, the only error code that we are going to respect from this rate limiting service is our 400 rate limit code. Everything else is just going to lead to a forward to this microservice, and all of that is good. Of course, we will operationally monitor this rate limiting service and have dashboards and stuff based on our observability here. Another benefit here within Envoy is that it does provide observability, service observability. So we can use this Envoy reverse proxy to help us with generating dashboards and alarms and all that kind of stuff, which allows us to monitor the health of our entire microservice architecture. So this is a really smart choice here. Latency, we want the rate limiter to be super fast. So we are adding a few layers here. We're adding this uh, Envoy reverse proxy, but this is super fast. This is implemented using C++, and it's designed to be extremely efficient. And so we just need to make sure that we scale it correctly with AWS App Mesh. It makes it really easy to manage that scaling. Um, then our rate limiting service here, we also need to make sure this is super fast. So we just want to build this with a really efficient implementation. But it's not actually doing a lot of work. Most of the work is done in Redis, but Redis has like microservice or microsecond response times, and all of this sliding window. If we want really, really fast, we can go with fixed window. That'll be even more efficient, but sliding window will also be extremely efficient as well. And so this actual additional stuff that we're doing here is very fast. Rate limiting service is basically just routing to Redis. All of the rate limiting logic is we're just doing a single key, like put to Redis, like check if rate limited on Redis. So and this, as we've established, is in memory and very, very fast. So all of that is good. So fault tolerant, we talked about that. Latency, yeah, we definitely have single digit millisecond latency there. Overhead in terms of adding our rate limiter scale, we want to scale to handle 1 billion calls per day. That's just a question of scaling up our cluster. We have Redis clustered and sharded based on the key, which is API user bucket. We can stick as many shards in Redis as we want. We can use Elasticache to be able to manage that Redis, and we can scale up and scale down as we need. Rate limiting service will also be horizontally scaled. It's behind a L4 load balancer. We'd probably have like a we'd probably either use most likely we would use like an EC2, have a warm EC2 service, and then just have um, a auto scaling group configured, and we just keep this warm for the amount of load that we want to expect. The other thing that we could do is we could add in a second layer of of rate limiting here at API gateway, and just make sure that even the load coming into rate limiting service is according to our expectations. So there's a trade-off there between practicality of having two different of having it's slightly more complex to have two different layers of rate limiting, one coarse grain and one fine grain. Um, but we could also so there's additional complexity, but that would reduce the incoming load to rate limiting service and make for a more um, optimized implementation. We wouldn't have to scale this as carefully because we have global rate limiting limits here. And this just can focus on per user per session rate limits. So that handles scale. We can scale to handle 10 billion calls per day. What does this actually look like? Let's do the math. So 1 billion calls per day. That's 100 divided by 100,000. That's 10K calls per second. So 10K calls per second. Rate limiting service, it's a modern EC2 instance. It's just forwarding these along to Redis. So we would probably just have this be, it would be CPU bound rather than memory or network bound because these are small. I we don't know the structure of the requests, but we're assuming that they're small requests, so they're CPU and network bound. It could even just be a single hash key if we have that passed along from our Envoy reverse proxy, and so could be a very tiny request that we're handling here, and so we are CPU bound. And I would say in practice with the CPU bound service like this, that's just talking to Redis, we could probably scale this up to handle 10,000 transactions per or calls per machine per second. And so we could potentially handle 10K calls per second with 3 machines, considering a multi availability zone. 10K is kind of upper bound for lightweight service on modern EC2. Maybe we can do better with some extreme tuning. Um, so 10K is kind of upper bound for lightweight service on modern EC2. We can handle with 3 hosts in 3 AZs. And then to be careful, I would just do 2 hosts in 3 AZs. 6 hosts is plenty scaled. So we would be able to handle peaks of 60,000 TPS, peaks of 60K TPS. So that should definitely handle our 1 billion calls per day, including peaks. So then one other thing I wanted to talk about here, we're a little bit out of time, but I think it's interesting. Just something to mention that I can't dig into I don't really have time to dig into details so much, but what we can also support here is because we're using AWS App Mesh and Envoy, we can introduce a sidecar pattern within these microservices. And what this sidecar is it's a deployment within alongside our microservice using like a container within within this hardware. And if these microservices are calling each other, what we can do is we can actually use this sidecar to intercept those network calls, and we can, in fact, um, do rate limiting again between these microservice calls. And what that does is that will allow us to essentially protect microservices from noisy neighbors. So what a noisy neighbor noisy neighbor is if one of these microservices starts like retrying a lot, like maybe one of these microservices goes down and another microservice does a lot of like aggressive retries and stuff like that. These sidecars can intercept that network traffic uh, and actually rate limit it according to rate limiting service here, or we can decide to add circuit breakers or something like that. And essentially, the AWS App Mesh is going to manage these sidecars as well as manage this reverse proxy. And so what we can do is we can make sure that all of these different microservices have similar configurations for how we do that. And all of this configuration on rate limit, resilience, circuit breakers, retries, etc., can be deployed dynamically. And so that allows us to react really fast in real time if we ever have some sort of issue impacting our service stack. And so this makes our microservice architecture with rate limiting extremely operationally reliable. um, it does add some overhead with the microservices. We have an additional environment which is deployed to all these microservices. It does have a non-zero overhead in terms of adding these service calls, and so we need to determine, do the operational benefits of adding this stuff outweigh the potential costs? Like if this is a really, really super tightly sensitive, some of these are super tightly sensitive latency operations, it may be best to not put one on one of this microservices, one or more of these microservices. And that's fine too. We can pick and choose which ones are more or less latency sensitive and apply the sidecar and the additional level of load balancing or sorry, the additional level of rate limiting accordingly. Um, and so all of that is pretty good. And I think that we've satisfied all of our non-functional requirements. We've satisfied all of our functional requirements. And uh, and I think this rate limiter design is pretty thorough at this point. So I am going to terminate here. And thank you so much for joining. And hope to see you tomorrow. I'll be talking about another system design problem then. So thanks for joining, and make sure to join my Discord channel as well if you have not. We talk about system design and LeetCode and job interview prep and all that fun stuff. So please join us there, and happy to trade mocks and all that kind of stuff. Thanks. Bye bye.